Good afternoon. So today we will begin the last part essentially of the chapter on series, which is also the most important one because what we learned so far were just the tools that we need to study one of the most important applications of series. Not the only application, but the most important one that we learn in this class, namely how do we actually use series to represent various types of functions, which is a very important application in analysis and a very useful one in many situations. If you want to see even more interesting examples of other types of representations, you can take, for example, a course in partial differential equations. And some of the stuff we learned today is going to be necessary to know in that course as well. But let's actually illustrate with a couple of examples. Let's call this a little introduction and motivation of the concept. What we mean by series representations of functions. So I'm going to actually remind you that we learn something called the geometric series. And it's important to remember this as a distinct example from all other series because it's the only series which we know what it converges to if it is convergent. All other series we learn in this class, we could only establish the convergence but not what they are equal to. So this series converges to a over 1 minus r if r, that ratio of the geometric series, is between -1 and 1. So notice that with this example of the geometric series, I can actually come up with a function that can be written in terms of a series under some conditions. For example, if I take, for instance, a to be 1 in this formula here from the geometric series, and I look at the function 1 over 1 minus x, I can recognize that this function is the sum of a geometric series with basically r equals x. You can replace r with x, and you could say that actually 1 over 1 minus x is equal to 1 plus x squared plus dot 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 x to the n, so equal to an infinite sum. I should start from 0 in this case, right, because it starts from 1, so the summation from n equal to 0 to infinity of x to the n. Only, so again, this equality is valid only if x is between -1 and 1. So I want you to pay attention that there is an advantage in the sense that we can replace a function with a series. And the advantage is because, just to state it right from the beginning, in general, it is easier from a calculus perspective to work with powers of x. So imagine you have a more complicated function. Not that this is overly complicated, but other ones might be more complicated. And all of a sudden you can replace it with basically x to the n, combinations of, I should say here, replace it with summation, because it's not just x to the n, so summation of x to the n, so powers of x to the n. So basically, if you want to integrate, for instance, the function or to differentiate, things can be as easy as, under some conditions of course, things can be as easy as integrating the power rule or differentiating the power rule, which is obviously as easy as it gets. You could also maybe approximate the function with, for example, a linear or a quadratic term. For instance, you could decide, for instance, to replace your function just with the first term, 3 terms in that series. So that you have just a quadratic to deal with, and if you're happy with the error, with the difference between the exact value and the polynomial, then you have the advantage of basically working with polynomials. So in general, polynomials are easy, relatively speaking, right, when you deal with them in calculus applications. But crucially, notice that often the ability to represent a function by a series is constrained by the interval of convergence. So 1 plus x squared plus x to the n, right, this thing converges only if -1 is x, only if x is between -1 and 1. So this equality is not valid for any x. You can't just replace this with 1 over 1 minus x for any x. Only if x is between minus 1 and 1. So you could try in Maple, for example, or if you don't have Maple, you could try, for example, Wolfram Alpha on the internet. You could, for example, enter the summation 1 plus 1 over 2 plus 1 over 2 squared dot 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 1 over 2 to the n, so an infinite sum, and the calculator should give you the answer 1 over 1 minus 1 half, which is exactly 2. 1 over 2 is going to be 2. But if you try, for example, to enter, let's say, 1 plus 1.5 plus 1.5 squared plus dot 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 1.5 to the n and so on, then you're going to get strange answers like infinity or divergent or doesn't exist or whatever. So in the other words, you're not going to get a real number. So you can just expect that this is going to be equal to 1 over 1 minus 1.5. Obviously, that's not true, right? Because it doesn't converge outside of the interval minus 1 and 1. On the other hand, and if you have a moment, you should try this right now. For example, again, if you try in Maple or Wolfram Alpha, if you try to enter, for instance, 1 plus, let's see, x over 1 factorial plus x squared over 2 factorial x to the n over n factorial, you might be surprised to notice that the computer will tell you that this is equal to e to the x without any restrictions on x. You can replace x with anything you want. The computer seems to say that, this summation, this infinite sum is e to that value of x. So this suggests that maybe this series converges for any x. So in other words, we could also have the nice situations in which the series that represents a function might be valid for any x, which is even better. So another thing I wanted to notice before we move on to the main definition and some examples, notice that both of these examples are essentially power series that involves power of x. Now the coefficients may not be just constants like in the case of a geometric series. Notice that in the case of a geometric series, those coefficients are all equal to a, whether a is 1 as in my example or any other value. But here the coefficients in case of 1 to the x were 1, 1 over n factorial, which is also 1, but it's written like that to see the pattern, 1 over 2 factorial, 1 over 3 factorial, 1 over n factorial, and so on. So there are powers of x, but the coefficients seem to be depending on n in general. So the question we're going to address is for series of this type, which we will define immediately, does it converge, this type of series? And if yes, to what values? And you will see that in all cases for this type of series, which will be called power series, the values will be actually an interval, just like in the case of the geometric series. And in the more generous case of e to the x, that interval could be basically all real numbers. But in general, you would expect an interval of convergence, which is extremely important to know, because if I want to use that series, I need to know what I'm allowed to plug in for x. So that it converges for that value. So without further ado, let's write down the definition of what we call a power series. So a power series is an infinite series of the form summation from 0 to infinity. We start from 0 by default in this definition. Cn, some number that may depend on n, x minus a to the power n. And if we expand this will be c naught plus c1 x minus a plus c2 x minus a squared and x minus a to the power n and so on. I should say here this is called the power series, a power series centered at a. that real number a. As an additional example, which will be dealt with separately in many examples, just as a point of, just as a particular case, if I have summation from 0 to infinity cn x to the n, so basically the case when a is 0, this obviously is centered at 0. A power series centered at 0. So the three examples before were of this format. Okay, so for example, the one for the e to the x, the one involving 1 plus x over 1 factorial, x squared over 2 factorial, and so on, that was centered at 0, and cn was 1 over n factorial. So in the next pages, we're going to basically go over these types of series and figure out when they converge. For what values of x they will converge. So stay tuned. Okay, so let's begin with an example similar to the one involving factorials. So suppose we have the summation from 0 to infinity x to the 2n over n factorial. And you can actually prove the one yourself with just the x to the n is very similar, obviously. And we kind of guessed already that since I already told you that that one converged for any x, converge for any x. Let's see if it's the same in this case. The way to go about it, so again, the question is to find what we're going to call later the interval of convergence. I'm kind of anticipating this because until you actually go over the proof on how to, whether it converges or not, you may not realize that it's going to be an interval. And I should write a couple of things before we do that, just as a preliminary stuff. We're going to work with absolute values as part of the ratio test, which is usually the one that works when you check power series convergence. So remember that if you take the absolute value of a product, that's the product of absolute values, so some algebra rules basically. And if you solve an inequality involving an absolute value, like for example, x minus a less than some number r, this is going to be equivalent to x minus a between r and minus r. And then if you add a on both sides, that's a minus r less than x less than a plus r. So this type of operations, these algebra rules, if you want, will appear often when you check for convergence of power series. So we're going to begin with the ratio test. Now remember, at this point, x is a real number. It can be positive or negative. And don't forget the absolute value when you come up with the ratio test. So in the ratio test, this stands for an. So we're going to take the quantity an plus 1 over an in the absolute values to see under what conditions or for which x in the limit has a limit less than 1. So remember, in the ratio test, the series will converge if the limit of this quantity is going to be strictly less than 1. If it's greater than 1, it will be divergent. If it's equal to 1, the test is inconclusive. So in this case, an plus 1 will be x to the power 2 quantity n plus 1 divided by n plus 1 factorial, then over an, which is the same as times the reciprocal of an, that's times n factorial over x to the 2n. So the idea is to take the limit as n goes to infinity, and that will give us essentially a limit in terms of x in general. And then we're going to figure out when that limit is less than 1. Right? So once again, we're basically using the ratio test. First, let's simplify this a little bit. Just like we did it in any ratio test before, we're going to combine the terms. Well, we're going to group them together. X to the 2n plus 1 is x to the 2n plus 2, right? If you distribute the 2. And then n factorial over n plus 1 factorial. X to the 2n goes away, and you're left with x squared on the top. N factorial goes away, and you're left with n plus 1 on the bottom. All right, so pay attention here because this is the moment when you have to really be careful on how to manipulate these terms. At this point, basically you can get rid of the absolute value, just in this case. Normally, we could at most pull out anything that depends on n out of the absolute value. So you could do it like that, based on the formula I just mentioned here on the top of the page, and n being positive, that's just 1 over n plus 1. And then you're left with something in terms of x inside the absolute value. Now, in this particular case, you can get rid of that absolute value as well, because x squared is also a positive number, positive or 0, right? So that quantity that came from the ratio test was just x squared over n plus 1. So as n goes to infinity, so the limit of as n goes to infinity of this quantity, which remember, this is just the limit in the ratio test. Later on, you can just draw an arrow and write the limit right away so that you don't waste too much time. So the limit as n goes to infinity, no matter what x is, remember x denotes a real number, this is just going to be some number over something that goes to infinity, so like a constant over infinity. This is going to be 0 for any x, for any real number x. So that 0 is less than 1, and that tells me this series converges for any x. So that's the easy case essentially with power series, when the limit gives you a number less than 1 no matter what x is. So that means summation from 0 to infinity x to the 2n over n factorial converges for any x. And because in general the interval of convergence will be an actual interval, not any real number, we will talk about what we call later the radius of convergence. But in this case, because the convergence is all real numbers, so you could write it as x between minus infinity and infinity, you could say that the radius of convergence is infinity. All right, and let's do another one. Another example, yeah. So this time a less trivial one. Well, this number 1 is not trivial, but one that doesn't give you all real numbers as an interval of convergence. So let's say I'm looking at the summation from 0 to infinity, x minus 1 to the n over, let's say, 2 to the n square root of n. Just like before, let's establish the ratio test. So the limit as n goes to infinity, an plus 1 over an in the absolute value. Remember, by an I mean the whole term in the summation. So that's going to be, let's see, x minus 1 to the n plus 1. I'm plugging in n plus 1 now. 2 to the n plus 1 square root of n plus 1 times 1 over an, which is 2 to the n square root of an over x minus 1 to the n. Let's again group the terms. Let's see, x minus 1 to the n plus 1 together with x minus 1 to the n. 2 to the n over 2 to the n plus 1, and then n over n plus 1 under the radical. All right, so notice x minus 1 to the n cancels out with x minus 1 to the n plus 1, and you're left with x minus 1 on the top. Keep that in mind. 2 to the n over 2 to the n plus 1, you're left with 2 on the bottom. And let's just pull this out of the absolute values, because you can pull out the positive constant out of the absolute value, right? So you can pull out 1/2 square root of n over n plus 1 absolute value of x minus 1. So I want you to notice in this configuration here, and I'll show you in a more general setting immediately, how you're left essentially, or you can isolate in this fashion, the term x minus 1 in the absolute value, because that's going to happen basically to pretty much any power series that, you know, is in that standard form. So basically the convergence of this series essentially depends on what this does when n goes to infinity. And then when you set this equal to, or make it less than 1, so that you figure out when it converges or not. All right, so again, x stands for a real number, remember. As n goes to infinity, the part that depends on n converges to 1 over 2 square root of 1, right? N over n plus 1 goes to 1. So basically the entire limit here is going to be 1 over 2 absolute value of x minus 1. All right, so let's not rush this. What we just did, we applied the ratio test. And in the process of the ratio test, we figure out the limit. And the limit in this case is going to be 1/2 square root of x minus 1. So the limit in the ratio test is expected to depend on x, because after all, your series depends on a real number x, which is part of the power series definition. So now it's just a matter of figuring out when this series converges. Well, the ratio test tells you that when this limit is strictly less than 1, it converges. It tells you it's absolutely convergent, basically. And that is equivalent if you leave just x minus 1 on the left side. So if you multiply by 2, that's going to be less than 2. Whenever you write the conditions of convergence at this stage in the game, with x minus 1 in the absolute value less than 2, this number 2 is called the radius of convergence. The reason it's called this way is because it will represent half the length of the interval of convergence. Because once we solve for x, you will end up with an interval of length 4, essentially, right? I mean, this will be half the length of that interval. In many problems, again, the question will be finding the radius of convergence and then the interval of convergence. So we have to move on to figure out the interval of convergence after this step. Remember, when you have that inequality, absolute value of x minus a less than r, in this case, that's equivalent to minus 2 less than x minus 1 less than 2. And if you add 1 on both sides, that'll be minus 2 plus 1, which is minus 1, less than x less than 3. All right, so this is the part that people sometimes forget if they don't pay attention what they're supposed to do in the end. Or if they don't remember that the ratio test gives you a case which doesn't give you an answer, neither convergent nor divergent. So remember, if the limit in the ratio test is less than 1, we have convergence. So we are ensured that the series converges for between minus 1 and 3. But remember, if the limit is equal to 1, the ratio test is inconclusive. And in this case, the limit will be 1 at the endpoints of the interval that you just found. For example, if x equal to minus 1, that limit, 1 over 2 absolute value of minus 1 is equal to 1. If x equals 3, the other endpoint, that limit above is 1/2 3 minus 1, which is again obviously 1. So the endpoints must be analyzed separately. We're going to do that on the next page so that we don't crowd it here. But before we move on to the next page, again, notice that, pay attention that we need to do this, because if we don't, we may miss points for which the series might converge as well. At this point, we know for sure it converges strictly between minus 1 and 3, but whether it converges for minus 1 or whether it converges for 3, it's still an open question. Right? The ratio test doesn't give us the answer in that situation because the limit will be 1. So then what we need to do is to plug in individually these endpoints into the series, and then use other convergence tests to figure out whether the series converges or not at those endpoints. So stay tuned to finalize this example. All right, so let's continue. We have convergence so far between -1 and 3. Radius of convergence is 2, right? Notice that half the length of the interval is 4. So 2 is going to be half the length of the interval. And it's called radius also because notice it's actually centered at 1. If I place here 1, you know, because the power series is centered at 1, the distance between 1 and 3 is 2. And the distance between -1 and 1 is also 2. That's why that number is called the radius of convergence. So let's analyze the endpoints. So what happens if x is equal to -1? I'm going to plug in -1 into the series. And notice that at this point, the series becomes an alternating series. -2 to the n. Do any simplification that may be possible. I can pull -1 to the n, 2 to the n, 2 to the n, 2 to the n cancels. By the way, you know already the ratio test doesn't work. Don't even try. That's why you are here in this particular case. And if it's an alternating series, the only tool at our disposal is to check convergence using the alternate series test. So this case is very trivial to do it via the AST. Just state the conditions so that the grader, myself in this case, will know that you know what you're talking about. So there are two conditions to check. You take the positive portion of the term here, that means 1 over root n, and notice is decreasing. We don't have to do much more than that. If n increases, the fraction decreases. Notice that 1 over root n goes to 0. So that means this is going to be convergent by the alternate series test. So it will converge for x equals -1. All right, so now the last part, let's check the right endpoint. If x equals 3, we go back to the series from 0 to infinity, 3 minus 1 to the n, 2 to the n root n. This becomes 2 to the n, 2 to the n over times root n. This cancels out, 1 over root n, or if you want, 1 over n to the 1/2. You should pause the video and try to figure out the argument, convergent or divergent, and via what test, because you should recognize these. I mean, basically just practice to see if you can recognize quickly which test you can apply. This is an obvious P series with P equals 1/2, which is less than or equal to 1. Hence, it's divergent. So we finally give the answer to the full problem. For this series, the radius of convergence is 2. The interval of convergence, which we're going to abbreviate IC later on, is closed interval at -1, because it converges at -1, but open at 3. Very important to make sure you write it down carefully this way. So if you have convergence at one of these endpoints, you need to write a closed interval at that endpoint so that you can include the actual value. Or you could write it like this. -1 less than or equal to x less than 3. But the endpoints must be included if it converges at those endpoints. All right, so with this in mind, let's move on with another example. This will be probably my last example, and I'm going to finalize it with a general framework of how these limits look like for any power series. So this is my third example, actually, I suppose. So we have summation from 0 to infinity. Well, let's say, the way I wrote this series, let's say from 1 to infinity. As with all series, remember, if you remove the first couple of terms, remember the convergence interval doesn't really change. So let's say minus 1 to the n minus 1, x to the n divided by n 5 to the n. And let's do again the ratio test. So we're going to have minus 1 to the n plus 1 minus 1. Carefully replace n with n plus 1 everywhere. And then divided by what was there before, minus 1 to the n minus 1 x to the n. Okay, so let's do some simplifications. We have, what do we have? Minus 1 to the n on the top. So let's actually group them one more time so we can clearly see them. You can get rid of the minus 1 because of the absolute value. With a little bit of practice, you could do this faster later on. 5 to the n plus 1, then n on the top, n plus 1, and of course x to the n plus 1 over x to the n. This will be centered at 0 if you noticed. Minus 1 to the n minus 1 goes away and you're left with minus 1. And 5 to the n over 5. Anything positive can be moved out of the absolute value. Absolute value of minus 1 is 1. So this my absolute, the remaining, any minus 1 to any power will become 1 essentially, right? If you apply the absolute value. Sorry, it's kind of a mess here. So I mean, you know, minus 1 to the n inside an absolute value is always 1. And then like I said, the positive part goes away, goes outside the absolute value. So you have 1 over 5, n over n plus 1 outside, and then absolute value of x remaining. Finally, we can compute the limit. This goes to 1. So you're left with 1 over 5 absolute value of x, and you let this less than 1 to identify the radius of convergence. So it will converge if it's strictly less than 1. And this is equivalent, of course, to absolute value of x strictly less than 5. So the radius of convergence is 5. We can establish that right away. And the interval for now, I mean, it's not a final interval because we still have to remember, check the endpoints, but x is between minus 5 and 5. So we know it converges between minus 5 and 5. So now we check the endpoints separately. X equals minus 5. We go back to the series. Minus 5 to the n. We have to be very careful here with simplification of those minus signs. So notice we have minus 1 to the n minus 1. We have another minus 1 to the n, 5 to the n. Now, 5 to the n goes away. What's left is actually not an alternating series. Look closely here. If I combine the minus 1s, I have to add the exponent. So n minus 1 plus n becomes 2n minus 1, which is always an odd number. So that means the top is always minus 1 over n, or minus the summation from 1 to infinity of 1 over n. It's a minus 1 multiplied outside by the series from 1 to infinity of 1 over n. We met this series before multiple times. Remember, this is divergent because it's a p series with p equals 1, which is less than or equal to 1. So as it turns out, at the left-hand point, now the series will diverge. Notice, unlike the previous example when it converged at the left-hand point, this one diverges at the left-hand point. Finally, let's plug in 5, the right-hand point, and the summation becomes minus 1 to the n minus 1, 5 to the n, n times 5 to the n. So I'm left with minus 1 to the n minus 1 over n. This is an alternating series. by the alternating series test, we notice that 1 over n is decreasing, 1 over n goes to 0, so therefore it is convergent. So, radius of convergence 5, established before, interval of convergence open at -5, close at 5. And you will see in the homework, there are other examples in which, for example, you could have convergence at both endpoints or divergence at both endpoints. The geometric series is such an example. The geometric series will diverge at both endpoints. So I want to finalize with a remark on how these limits look like in general, just to see what you would expect. Because there is some similarity, I hope you noticed. In more cases, you notice that you could isolate these terms, absolute value of x minus a. And that's not an accident when you write down the ratio test. So stay tuned for a short last remark. So because these limits in the ratio test for power series kind of look the same, you could actually go about slightly differently. This is kind of optional, but you could do that if you want. So in general, if I have a power series in that standard format I mentioned, so with the coefficient Cn and A unspecified. So in this case, the ratio test, so if you take the limit as n goes to infinity, and so it's going to be absolute value of Cn plus 1 x minus a to the n plus 1 divided by Cn x minus a to the n. So in the ratio test, if you simplify this, notice you could separate Cn plus 1 over Cn with the absolute value of x minus a. And assuming that the limit is a real number of Cn plus 1 and Cn, so assuming that actually this piece here converges to a real number not equal to 0, so a real number not equal to 0, whoops, this looks like, so real number not equal to 0. You can basically denote, let's see, you can actually denote it by 1 over r, because it's going to be basically 1 over the radius of convergence. If that's the case, then the entire limit, because remember, you compute the limit as n goes to infinity. So basically the limit will be 1 over r absolute value of x minus a. And this will be, of course, less than 1 if absolute value of x minus a is less than r. So in other words, that r that I'm talking about, which comes from this multiplication by that absolute value, is in fact the limit as n goes to infinity of Cn over Cn plus 1. So you could actually compute the radius of convergence directly by computing that limit. So it's a little bit faster if you prefer, but it's not really that much faster. So I actually don't use that in practice, but I wanted to point out that you know, you always end up essentially with pulling up this part here when it converges to a real number outside of the absolute values, and then you take the limit as n goes to infinity, and you end up essentially with absolute value of x minus a times some real number, and that real number ends up being the reciprocal of the radius of convergence, because if you move it to the right hand side, it's going to be, you multiply it by r, so to make it just x minus a on the left side. If you want to see, for example, if you look at the previous example, let's see, I'm going to look at maybe the second example before. So we had summation from 0 to infinity x minus 1 to the n over 2 to the n square root of n. So we know that from what we did last time that the radius of convergence was 2. So you could apply what I just wrote here by simply saying, okay, the coefficient for this power series is 1 over 2 to the n square root of n. The radius of convergence is the limit of the absolute value of Cn over Cn plus 1. So you're going to just do, here the absolute value doesn't have any meaning because these are positive numbers. So it's going to be 1 over 2 to the n square root of n divided by 1 over 2 to the n plus 1 square root of n plus 1. And simplify this a little bit. 2 to the n cancels, and you're left with 2 on the top, and this approaches 2, right? Because root n plus 1 over n approaches 1. So the radius of convergence is 2, and then you can plug in the endpoints after you solve the inequality x minus 1 less than 2, and then do the work like in the previous case, right? So minus 2 plus 1, minus 1, and then of course check minus 1 and 3 separately. This is really optional. It's not really that much difference in terms of how much time you spend, but this kind of gives you a formula, a generic formula for the radius of convergence, provided that limit exists. And I think that's it for today. I'll see you next time.